So this video is the second video for reviewing exponential and logarithmic functions, and as well as we're going to be reviewing solving exponential and logarithmic equations. So in the first video, we reviewed what an exponential function is, and now we're going to review what a logarithmic function is. So note that exponential functions are one-to-one functions, right? They pass both the horizontal and the vertical line test, or I should say the vertical and the horizontal line test, right? Because the vertical line test means that they are functions, that every input corresponds to exactly one output. And then passing the horizontal line test means that every input corresponds to exactly one output and every output corresponds to exactly one input, okay? And you guys should remember that when functions are one-to-one functions, it means that they have an inverse function and they are the inverse of another function. So that means that exponential functions have an inverse function, and actually their inverse are logarithmic functions. So if we were to graph f of x equals 2 to the x, and we can just think about plotting some points. So if we were to plug in, how about negative 2? So f of negative 2 would be 2 to the negative second power, which would end up being an output of 1/4. If we plug in negative 1, we would get 1/2. If we plug in 0, we get 1. If we plug in 1, we get 2. We plug in 2, we get 4, and we plug in 3, we get 8. So what I've just drawn is the function f of x equals 2 to the x, the exponential function. And end behavior, so if we thought about taking the limit of f of x as x approaches negative infinity, the function would end up approaching 0, meaning there is a horizontal asymptote at y equals to 0. And as x approaches positive infinity, the function approaches positive infinity. Now, we can determine what f inverse looks like just from switching all the x and the y coordinates, right? Because when two functions are inverses of each other, it means that their domain and ranges flip-flop. So the domain of one function is actually the range of the other function. So for example, when I usually introduce inverse functions, I usually draw the little function machine that you used back in like Algebra 1 when you first started talking about functions. Okay, so this in purple will be my f inverse, the inverse of the function f. So if we were to take, how about negative 2 and input it into f, we said that the output was 1/4. So that means that if we were to take 1/4 and input into f inverse, we would get an output of negative 2. So the point 1/4 comma negative 2 lies on the graph of f inverse. So just an approximation there. So I can just think about flip-flopping each of the x and the y coordinates. So negative 1, 1/2 would become 1/2 negative 1. 0, 1 would be 1, 0. 1, 2 would be 2, 1. 2, 4 is 4, 2. And 3, 8 would then map to 8, 3. So this is what the graph of f inverse would end up looking like. But what would the equation of f inverse be? Well, remember for finding a function's inverse, you switch the x and the y coordinate. So I'm going to rewrite the exponential function as y equals 2 to the x power. And then think about switching x and y. And then we have to solve for y. Well, in order to solve for y, because y is in the exponent position, we can think about taking the log base 2 of each side of the equation in order to get the y out of the exponent position. So the right-hand side would just end up simplifying to be y. So that is log base 2 of x is f inverse, right? Y could be replaced with the function notation. So the function name f inverse. Let me move this. So f inverse equals to log base 2 of x. And like the inverse of y equals 3 to the x would be y equals log base 3 of x. Last thing on this graph is since f of x had a horizontal asymptote at y equals to 0, that means that f inverse actually has a vertical asymptote at x equals to 0, right? Because the x and the y's switch. Okay, so here is our definition of a logarithmic function. I always like to draw the arrows to help me. So for x greater than 0, b greater than 0, and b not equal to 1. And these restrictions go back to our definition of an exponential function. The logarithmic function with base b is denoted as y equals to the log base b of x, where this statement is true. And basically what this statement says is that every logarithmic function can be rewritten in exponential form. So it says that y equals to log base b of x if and only if x is equal to b to the y power. And the way I like to think of rewriting in exponential form, the logarithmic statement, is thinking, okay, b to the y power is equal to x. And we read it log base b of x. Okay, so it's important to know how to go from logarithmic to exponential form, because that's one technique that we could use for solving some equations. So here, let's use another color. To rewrite log base 2 of 8 equals to 3, right? It's a true statement, and it would probably register more looking at it in its equivalent exponential form. So 2 cubed is equal to 8, which is true. 4 to the 1/2 power is equal to 2. 7 to the negative 2nd power is equal to 1/49. Okay, all three of those are the equivalent exponential form of the logarithmic statement. And then you should also be comfortable going from exponential to logarithmic form. So 64 equals to 8 squared can be written as log base 8 of 64 equals to 2. And I always think about checking it by thinking about the arrows. The log, right? 8 squared equals to 64. And remember, the square root can be thought of as the 1/2 power. So log base 169 of 13 equals to 1/2, right? Because 169 to the 1/2 power equals 13. And the last statement, 1/25 equals 5 to the negative 2nd power. Well, that would be log base 5 of 1 over 25 equals to negative 2. And then we can think about exponential form in order to help us with evaluating logarithms. That's kind of how I think of it. You don't have to. But like when I want to find the log base 6 of 36, I'm thinking, okay, well, 6 to what power would be equal to 36? And that would be 2. So you're thinking about like what power could you raise the base to be equal to what the argument of the logarithm is. So 4 to what power would be equal to 1/4? Well, that would be -1. 5 to the third power, 5 cubed, is equal to 125. Therefore, log base 5 of 125 equals to 3. Okay, and the logarithmic function of base 10 is known as the common log function and is expressed as y equals to the log of x. When you don't see the base written, but it's still written as log, that means log base 10. And then the natural logarithmic function has is notated as y equals ln of x, or you can read that as y equals natural log of x, and that would be base e. So ln is the same as log base e of x, okay? And both log base 10 and ln are buttons that are on the calculator because they're commonly used. If you, on the TI-84, if you hit the second button in either of those buttons, then you're calling up 10 to the x power or e to the x power. And then those two functions, so because they're so common, but then you can also just call up log on your calculator if you hit the math button and you scroll up. On my calculator, it's A. So if you have a newer TI-84, not a really old one, you'll have the option for log base, and then you can type in what you want your base be and your argument to be in order to evaluate. Okay, and then just kind of to summarize, give you a graphic to summarize. So we've talked about exponential functions and logarithmic functions. They are inverse functions of each other. So y equals to b to the x is the inverse, or its inverse is y equals log base b of x. And then just some key facts about each of those types of functions. Okay, so I'm going to make a third video to